Today in section 2.2's notes, we're going to talk about density curves and the normal distribution. Our first objective is we want to be able to connect the density curve to the shape of a histogram or stem plot, and we want to be able to describe the shape of a distribution, and we want to be able to identify important information from a distribution. Okay, so our density curve is any kind of curve, but what we've got to be careful of is it doesn't have to be curvy. It could be boxy, like this here. This is called a density curve. Technically, anything that's graphing a compact picture of the overall pattern of data is a density curve. Okay, a couple key points about a density curve is that a density curve is always on or above the horizontal axis. It always has an area of exactly 1 underneath it. Okay, the area of the curve is the proportion or percentage of observations that fall in that range. So if you think about this density curve here, there could be an infinite number of data points. Think about the dot plots we've been doing. We could have infinite number of data points. So we just draw a curve to represent those data points. Okay, so we don't have to figure out exactly how many are underneath. There is no real set of data that is exactly described by a density curve. This is an approximation. All right, so right here, it's an approximation that is practical to use. When we have this, a median of any density curve or any curve, all right, or boxy kind of curve or pointed, we'll do a bunch of different ones. The median of any density curve is your equal areas point. It's the point that divides the area in the curve in half. All right, so where does it take the curve and break it? Where it's 50% of the data points are lower, 50% of the data points are higher. The mean is your balance point, at which point the curve would balance if made of solid material. Okay, literally like a balance beam or a teeter-totter when you were a kid, right? The teeter-totter or seesaw, the balance beam was right in the middle, so you don't tip one way or the other, all right? Even if your siblings make you tip, like mine did, or I did to them. But when you think about it, if you had the teeter-totter where it wasn't, or the seesaw exactly in the middle, right, then you would never get the other side off the ground. It would always be too heavy or too light on one side or the other because it wasn't exactly in the middle. Now, with this, let's take a look at this density curve. All right, with this density curve here, it has 0 to 2 on the x-axis and a height of 0.5. So when we're looking at it, if we want to verify that the graph above is a valid density curve, this is asking us to just confirm that the area under the curve is 1. So if you're verifying, you're confirming that the area under the curve is a 1. This is a rectangle. So since it's a rectangle, we can say, we can just use the area formula. Okay, the area is length times width, or width times length, however you look at it. So 0.5 times 2 equals 1. That's our verification. So that means it's legitimate. Now it's saying what percent of the observations lie below 0.3? Well, 0.3 is right here. So we want below 0.3. So this is a mini rectangle here. That's 0.3 by 0.5. So 0.3 times 0.5 is going to give us 0.15 or 15% because it asks for percentage. What percent of the observations lie above 1.2? Well, 1.2 is going to be right here. So when you figure out this rectangle, okay, it's going to be from 1.2 to 2 and then 0.5 tall. So I got 0.8. This space is 0.8. This space is 0.5. 0.8 times 0.5 is 40%. What percent of the observations lie between 0.6 and 1.6? So from 0.6 to 1.6 is 1. It's this distance of 1, so 1 times 0.5 is 50%. The median, since this is a symmetrical, uniform density curve, your median is literally the middle, 1. Right? At 1, it's going to break this rectangle where it's 50% this way and 50% this way because it just goes from 0 to 2. We're going to practice more. You'll see it in your bookwork of different problems that are more than that. Okay. And then when it's saying what are Q1 and Q3 of this density curve, well, Q1, if this is the median, right, then half of this is Q1, 0.5. And if this is the median, then half of this is Q3, 1.5. And that's why I have that Q1 is 0.5 and Q3 is 1.5. Now, this concept of like figuring out the area, right, works for any density curve out there. And you'll see a bunch of different ones that we're going to go through. Like later, we have one. Where did I put that guy? We'll talk about this one in class. This is in your packet. We'll talk about this guy later, and we're going to go through a bunch of different curves. Your homework, the bookwork has a bunch of different ones. But your most famous curve is your normal curve. All right, this is the be-all, end-all, big kahuna for us. So here's your normal distribution. It's a bell curve. Your normal distribution is bell-shaped. Your mean, median, and mode are all equal. They're all located at the center, all right, which is why I put mu here, which means that 50% of your data points are here and 50% of your data points lie above. It's unimodal, meaning there's one mode right at the middle, all right? It's symmetric. It's continuous. There's no gaps or holes. The curve never touches the x-axis. Technically, it doesn't close, but lots of times you'll see it close like that. That's okay. But technically, these are going to get closer and closer and closer and closer to the x-axis, and closer and closer and closer and closer. And it would technically like continue on forever. But the area between the curve and the x-axis is so incredibly minuscule that for our Stats 101 level, we're not going to worry about the tiny, 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 tiny details, okay? It is definitely used, but much more technical than our entry to stat class, all right? And our total area under the curve is equal to 100%, which is why I have 50%, 50%. This is a big deal. Your empirical rule, which you would have learned in psychology if you took psychology, all right, is that when we have our mean in the middle, then we have 3 percentages that we're going to use all the time. Okay, 68%, 95%, 99.7%. If you go from the mean within 1 standard deviation, okay, from the mean, this should really say from the mean, within 1 standard deviation, you have 68% of your data every time. So I drew that here. If you draw your normal curve and you put the mean in the middle and you go up 1 standard deviation and down 1 standard deviation, then you're going to have 68% of your data points in here. Since this is symmetrical, we could say it's 34 here, 0.34 or 34%, and 34 here, 0.34 or 34%. Okay, so that will give us our center 68%. Well, within 2 standard deviations of the mean is about 95% of your data points. Right, you can think of it of your data points. So if I have my curve here and my mean is here, this time I'm going to go up 1, 2. I'm going to add 2 standard deviations, and I'm going to go down 1, 2. You'll notice, didn't it get wider? Right? It's wider than this area. So if you go this way, this is about 95% of your data points. Well, if the whole curve adds up to 100%, 95%, 100% minus 95 is equal to 5% left over. 5% left over, we have these 2 tails here. These 2 tails we could have as take our 5% and cut it in half. We could have 2.5% in each tail. So if we're talking, and I'm going to show you lots of application problems with this. This is huge. But if we have this line here, we could really have 2.5% or greater than here. 2.5% of data points are less than here when we have 2 standard deviations. If we come back to this, we could use the same concept. If this is 68%, right, then 100 minus 68 leaves us with 32. Cut 32 in half and we're left with 16%. That would mean that this is 16%. This is 16%. Well, if you use your logic, this is 50% because it's half of the graph. And this is 50%. 34 and 16 add up to half of the graph. You're allowed to write 50%, or you can put 0.5, 0.5. But don't mix and match. Like, you can't write, if you write 0.5%, that is completely different than 0.5, which equals 50%. So you have to be extremely careful with your notation as well. Now, the third rule with the empirical rule is within 3 standard deviations. Think about how much wide. We're going to go one more, so it's going to go even wider. So if we go one more, right, and you put your mean in the middle, you go 1, 2, 3 standard deviations, and you go 1, 2, 3 standard deviations. From here to here is virtually the entire graph. Well, that makes sense. It's 99.7%. We're going to have 0.3% cut in half is going to leave us with 0.15% for each tail. 0.15%, 0.15% in this tail, which is going to get us our leftover 0.3%. So if you go up 3 standard deviations and you go down 3 standard deviations, then that would be that. So, Ms. Michael, how does this get applied? Well, let's talk about women. All right, we'll talk about women first. So, heights of people are normally distributed. Women are their own normal curve. Men have their own normal curve. So, the general consensus is that the average height of women is approximately 5'4", okay, or 64 inches tall. And there's an approximate standard deviation of 3 inches. All right. So if we were to say, okay, between what values will the middle 68% of American women fall, then what we're going to do is we're going to draw a curve. And we're going to say to ourselves, how many standard deviations is 68%? 1, okay, because 68% is 1 standard deviation according to our empirical rule. So I'm going to put my mean in the middle, 64. I'm going to go up 1 standard deviation and down 1 standard deviation. How much is our standard deviation this time? Our mean is 64 and our standard deviation is 3. So I'm going to go add 3 inches, which is 1 standard deviation. That'll put me at 67. I'm going to go down 3 inches and that'll put me at 61, which means that the middle, right, here's our window, the middle 68% of American women are between 61 inches and 67 inches, which is really 5'1" and 5'7". And that should be logical, right? 68% of grown women, not people who are still growing, but fully grown, that's a logical window to be in. All right. Okay. Now, this is saying what's your tallest 2.5% of women? Your tallest 2.5% of women are taller than what height? Well, 2.5% isn't one of our 68, 95, 99.7. But we talked about the tails as well. 2.5% is a tail for 95%. So you say, okay, I know 2.5 pairs with 95. So I need to go 2 standard deviations. So the first thing I'm going to do is I'm going to draw my mean, 64. Now I'm going to go up 1, 2 standard deviations. I'm going to add 3, subtract 3, subtract 3. All right. That will put me at 64 plus 6 is 70 inches. And I'm going to go 64 minus 6 puts me at 58 inches. All right. But this is asking, so this is my 95% in the middle. The tallest 2.5% of women are taller than what height? This is 2.5% of women. They are taller than 70 inches or 5'10". And that should be logical. Taller than 5'10" makes sense that you're in the top 2.5% of heights. All right. So let's go back through. All right. The shortest 16% of women are shorter than what height? Well, what value was 16%? All right. Like which one did that pair up with? 16% paired up with, if I put my mean at 64, 16% paired up with 68%. This is 16 in each tail, the rest of the 32. So if we want shortest women, that's going to be on the left. 16% was up and down 1 standard deviation. So I'm going to go down 1 standard deviation, subtract 3, 1 standard deviation worth 3. And I'm going to say, all right, 64 minus 3 leaves me with 61. this would be the area I'm talking about. This is the bottom 16%. So it's shorter than 61 inches or 5 foot 1 inch. Okay. Between what values will the middle 99.7% of American women fall? So 99.7% means we're going to go up and down 3 standard deviations. 1, 2, 3. Add 3, add 3, add 3. 3 standard deviations, each are 3 inches big. 64 plus 9 gives me what? 73 inches. Okay. And then I'm going to go down 3. All right, so I'm going to subtract 3, subtract 3, subtract 3. And that's going to leave me with, brings me down to 61, brings me down to 58, brings me down to 55. Okay, so the answer is between 55 inches and 73 inches. If we convert that over to feet, so it's logical, okay, 60 inches is 5 feet tall, so this is going to be 4 foot 7 and 6 foot 3. 99% of American women are going to fall between 4'7" and 6'3". I hope that makes sense because I don't know very many women who are shorter than this or taller than this. All right, gentlemen, we'll talk about your heights later too, but it's typically reported that the average height is 5'10" with a standard deviation. No, wait, is it 5'10"? It might be 5'7". I'm going to need to research. I'll research and I'll let you guys know. I believe it might be, I think it's 5'10". Yeah, I think it's 5'10". And so we can go from there, all right? So I'm going to do another video because this one's getting kind of long to teach you about something else that's when it's not empirical rules.